Hello everyone, my name is Sanjeev Das. On behalf of my collaborators, I would like to present our work on building a flexible framework for expediting bug finding by leveraging past misbehavior to discover new bugs. This work was done at UNC. Fuzzing has emerged as the preeminent automated technique for finding vulnerabilities in software. Since the foundation led by Miller et al., various fuzzing approaches have been developed. And in recent few years, we have seen lots of great work in fuzzing that have advanced the field further, ranging from black box approaches that perform random input testing to gray box approaches which leverage execution information to guide fuzzing, and white box approaches that use advanced techniques such as symbolic execution. The success of gray box fuzzers largely stems from the fact that they use feedback mechanism to prioritize the inputs. Of all the fuzzing approaches, coverage-guided fuzzing has been the most prominent approach. It aims to increase the program coverage to eventually reach the buggy path. Typically, it tracks branch coverage to select interesting inputs to mutate further during fuzzing process. Let's look at how we do fuzzing in practice. First, we collect some seed inputs for a program that we want to fuzz. Then we run multiple fuzzer instances in parallel on a massive infrastructure. After running for a substantial number of CPU cycles, we may get large number of crashes. Then we invest significant effort on crash triaging to deduplicate the crashes, to find out if the crashes are unique, then is the bug critical, and is it exploitable? As commonly seen, once the fuzzer gets the first crash, subsequently many unique crashes are collected. But in fact, they are often triggered by the same bug. As shown in figure, more than 200 crashes are generated, but they are triggered by just two bugs. As highlighted by a recent study, improving bug finding linearly requires exponentially more computational resources. In other words, even though rediscovering the same vulnerability is cheap, but finding new vulnerabilities is expensive. Given these problems, we investigate the opportunities that can improve fuzzing process. There has been lots of work in each of these topics. In this work, we focus on fuzzing framework and crash deduplication. The contemporary coverage guided principle is inefficient in finding bugs, primarily because they give equal priority to all the program paths. Any input that triggers new branch edge is considered interesting. As shown in figure, to reach the bug, giving equal priority to all the paths may not be efficient. It slows the bug discovery. Another reason for this inefficiency is due to limited coverage metric. The coverage metric can significantly change the fuzzing performance. Many approaches track branch edge, but they lack contextual information of the paths. Recent works utilize more information, such as memory uses, rare branches. Studies show that, given same amount of resources, all the coverage metrics offer merit relative to flipping certain types of bytes, and in finding vulnerabilities not readily found by others. Different coverage metrics perform better on other benchmarks, underscoring the enormous diversity that exists between different programs. This raises an important concern: what signal can we extract from the execution to efficiently fuzz a program? In this work, we propose three extensions geared toward expediting bug finding and finding more bugs. One, microarchitectural information as a signal to build a coverage metric tailored for a specific application. Two, vulnerability-aware input selection. Three, configurable input selection strategy. Next, I'll explain each of them in detail. We use microarchitectural information obtained through hardware performance counters to build a coverage metric tailored for a specific program. Hardware performance counters are a set of special registers in CPU used to monitor and measure events such as instructions, branches, memory, cache, etc., and have been widely used in application domains such as debugging, performance analysis, and security. HPC provides valuable information specifically relevant in the fuzzing context. For example, we can profile deeper code paths through retired branches, less explored branches through branch misses, loop operations through loop stream microbes, and memory instructions. Moreover, all this information can be obtained at a low overhead. There are many HPC events, but only limited number of events can be monitored simultaneously because of limited hardware counters, typically 4. Therefore, the key challenge is to select a set of HPC events that would be best suited as a coverage metric for our program. Another important question is, how can we use fuzzing, HPC information, to guide fuzzing? To address these challenges, we infer knowledge from the recent works. Recent studies shows that similar vulnerability persists in widely used software and does not decrease over time. Based on similar intuition, code analysis platforms have been effective in using knowledge from known vulnerabilities to find the new ones. This brings to our second extension, vulnerability-aware selection of a coverage metric. Our conjecture is that the bugs in the earlier version of our program can provide a good signal to find similar or dissimilar bugs in the newer version. As much of the foundational code remains the same in newer version, similar coding practices are followed, which often leads to similar mistakes being repeated in the newer version. Our approach is named as OmniFuzz, that is fuzz in multiple directions. It has 3 stages. Pre-processing involves data collection, that is crashing and non-crashing inputs on older version of a program, and profiling HPC information. Model building involves feature selection using HPC events and heuristic generation using machine learning approach. Vulnerability exploration provides configurable input selection strategies to fuzz in different directions. Now I'll describe the key components of our approach. To perform feature selection, first we obtain crashing and non-crashing inputs on older version of the program. Then we profile HPC events corresponding to each input. Only 4 events can be monitored simultaneously because of limited counters. Next, we perform feature selection. To select HPC events, we observe the information gain of each event in identifying crashing and non-crashing inputs. As shown in figure, a few inputs, 8 to 16, have high information gain. We also observe that top events differ across various programs, underlying the fact that the code bases of programs are diverse. For example, top events differ for 2 similar programs, such as libgpeg and libpng. Using HPC events as features, we employ machine learning approach to build a classifier that can be used as a heuristic to perform input selection during fuzzing. Limited by 4 counters, we use up to 4 events with high information gain to build a machine learning classifier. Our analysis show that model with 4 events perform better than with 1 event. More importantly, top 4 events and next 4 events have higher classification accuracy in identifying crashing and non-crashing inputs. These sets of events can be used as coverage metrics. We choose multilayer perceptron to build a classifier as it has high classification accuracy and offers low runtime overhead. Instead of solely using crash deduplication for post-processing, we use on-the-fly crash deduplication to actively steer the course of fuzzing. When the fuzzer does not make a progress in finding crash or finding only similar crashes, the online deduplication mechanism can provide feedback to switch the fuzzing strategy. We can therefore switch our coverage metric to select a different set of HPC events to efficiently guide fuzzing. Given our understanding of the past vulnerabilities, we can essentially fuzz towards finding similar bugs as past and towards different bugs than the past. We saw this using the illustration. For example, for similar bugs, both the base fuzzer and HPC heuristic should classify the input as interesting. Only then the input is selected. Whereas for dissimilar bugs, HPC heuristic should classify it as uninteresting. In dual mode, we can switch the fuzzing strategy by selecting a different coverage metric when the fuzzer does not make a progress. We extended our approach on 3 state-of-the-art fuzzers and evaluated on 8 heavily fuzzed libraries. For ground truth, we manually analyzed and verified all the bugs. Next, we discuss results on bug expediency and bug discovery. Here we present results of our extension on AFL and MOpt fuzzer. To evaluate expediency, we measure relative speed up to a predefined granularity, which is essential from practitioner's point of view. For example, a crash obtained in first few seconds versus 15 minutes does not matter for a practitioner. Therefore, we consider the relative speed up to be 1. Our results show that, on average, our approach finds unique crashes more than 3 times faster while exploring significantly less paths than the base approaches. For comprehensive results, please read the paper. In terms of bug discovery, our approach finds 3 additional bugs on AFL and 5 on MOpt that are missed by the base fuzzers. We also found some new vulnerabilities in heavily fuzzed programs using our approach. In conclusion, HPC provides wealth of information that can help to build coverage metric tailored for a specific program. To learn more, please read our paper. Thank you for listening.